Hey everyone, this video is a rather short lesson. It's on scientific notation. So scientific notation is a way of writing very large numbers or very small numbers in a more convenient way. So for example, let's say you have the speed of light, okay, which is 300,000 kilometers per second. Okay, you turn on a light bulb. How long does it take for that light to get to the other side of the room? Well, that light travels at 300,000 kilometers a second, very fast, which is why it seems like the whole room lights up instantaneously. It's a very large number. It's even larger if you write it in meters per second. Okay? You could also have very small numbers, okay, like the wavelength of red light, which is 0.0000007 meters. It looks very small, but the wavelength of other colors is even smaller than that. Okay? That's why you can see a red light from farther away. You can see it more clearly in the darkness or in fog, for example. So all over the world, okay, in all fields of science, and in biology and physics and chemistry and in population, right, like the populations of countries, of cities, of the planet, okay, you're dealing with very large numbers a lot of the time, especially in biology and physics. Sometimes you're dealing with small numbers. So we want a more convenient way to write that down, right? And what's inconvenient about these numbers is you have a lot of zeros, either in front of the number or behind the number. And do we really need that many zeros? Well, turns out we don't, okay? Let's say, for example, we have a number like 300,000. Well, that's equal to 3 times 100,000. Well, 100,000 is just 10 to the power of 5. It's 10 multiplied by itself 5 times. Any number that is a 1 with a bunch of zeros, let's say there are a zeros after that 1, that's just 10 to the power of a. Okay. 10 to the power of 1 is 10. 10 to the power of 2 is 100. 10 to the power of 3 is 1,000. You get the picture. Okay. So if you have a number like 300,000, by recognizing that that's just 3 times 100,000, you can write that as 3 times 10 to the power of 5. That's scientific notation. Okay? Scientific notation is you have a number times 10 to the power of some other number. Okay? And the standard way of writing it is that your leading number, the a here, is less than 10. Now, what I mean by that is, let's take the population of the United States. 330 million people. Well, you could write that as 33 and then 7 zeros. 33 times 10 million. Right? There's your 7 zeros. But you could also write that as 3.3 times 100 million. Right? 330 million is 3.3 hundred million. Okay? So one would look like 33 times 10 to the power of 7. The other one would look like 3.3 times 10 to the power of 8. And that second way, that's the standard way of writing it. Both are correct. Both refer to the same value, but the standard way of writing it is that your leading number there, that it is less than 10. Okay? And also, more specifically than that, it is greater than 1. Okay? Because you could also, let me just put a box around that. You could also write down this same value as 0.33 times 1 billion, which would be 0.33 times 10 to the power of 9. Again, this is the same value, but the standard way to write it is that your leading number is greater than 1 and less than 10. It's just a standard, and frankly, it does look more neat, more compact. That's the point of scientific notation, to write things in a simpler to look at way. Now, you might notice that what changes here is the decimal spot, right? The decimal spot is between the 3's or in front of the 3's or, well, behind the 3's if you have 33.0, and that changes the exponent, right? And you probably remember this rule that each time you multiply a value by 10, you move your decimal spot over to the right, and each time you divide by 10, you move this decimal spot over to the left. We're actually going to use that, okay? Because here's what's happening. If you recall any number, let's say 236.52, okay? Well, that equals 2 times 100 plus 3 times 10 plus 6 plus 5 divided by 10 plus 2 divided by 100. Okay? And the decimal spot goes right after the number that is multiplied by 1, or the number that's not multiplied or divided by anything. Now what happens when we multiply this by 10? $236.52 times 10 gives us, well, all of that is being multiplied by 10. 2 times 100 plus 3 times 10 plus 6 plus 5, which is being divided by 10, plus 2, which is being divided by 100. All of that is being multiplied by 10. So what do we have? 2 times 100 times 10 plus 3 times 10 plus 6. Oh, almost forgot the extra 10 there. Times 10 plus 6 times 10 plus 5 over 10 times 10 plus 2 over 100 times 10. So what we have is 2 times 1,000 plus 3 times 100 plus 6 times 10 plus 5 times 10 divided by 10. That cancels out. So that's just a plus 5. And then plus 2, well, you have 10 divided by 100, which is like 10 divided by 10 times 10. 2 of them cancel out. So you have 2 times 1 over 10. We put that back in decimal form. We have 2,365.2. The decimal spot is after the number that's multiplied by 1. And if you look at our original number, 236.52, our decimal spot just moved over 1 to the left because we multiplied by 10. That's where that rule comes from. That's why multiplying by 10 is just moving your decimal spot over by 1. That's why multiplying a whole number by 10 is like adding a 0, because your decimal spot moves over by 1, and you have an extra 0 on the end. Similarly, if we divide by 10, let's say you have 25.2, and we divide this by 10, what do we have? Well, we have 2 times 10 plus 5 plus 2 divided by 10. All of that is being divided by 10. So we have 2 times 10 divided by 10 plus 5 divided by 10 plus 2 divided by 10 divided by 10. And we end up with these 10s are canceling out, so we just have 2 plus 5 divided by 10 plus 2 divided by 100. Right? Fraction multiplication. Multiply the tops, multiply the bottoms, 1 over 100. And what we have, once we return back to decimal form, is 2.52. The decimal is after the number that's being multiplied by 1. And if you look at the number we started with, before dividing it by 10, we're just moving the decimal spot over to the left. So, multiplying by 10, you move your decimal spot over to the right. Dividing by 10, you move your decimal spot over to the left. So if you have a number like 0.000007, well, that is 7 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, except it's a negative 7 because you're dividing. And when your exponent is negative, it means you are dividing by the base to the exponent. Okay. Some base to a negative exponent, it means 1 divided the base to that exponent. For example, 10 to the power negative 7 means 1 divided by 10 to the power of 7. So once we start using scientific notation, it becomes not only easier to look at very large numbers or very small numbers, it also makes it easier for us to multiply them and to divide them. So for example, if we have 3.3 times 10 to the power of, what was our value? I believe it was 8. 8 times 7 times 10 to the power of negative 7. Well, we can do that simply. Remember, we can multiply in any order. So 3.3 times 7 times 10 to the power of 8 times 10 to the power of negative 7. And now we have 10 to the power of 8 times 10 to the power of negative 7. Well, that just becomes 10 to the power of 1. Okay? Because when we have the same base in exponents and we multiply them, we're just adding the exponents. B to the power of A plus C. And that comes from the definition of exponents. We're multiplying A B's by C B's. How many B's are we multiplying by in total? A plus C of them. Okay? Let's say we are dividing. Okay? B to the power of A times B to the power of negative C. Okay? Well, what does that mean? Right? It means B to the power of A divided by b to the power of c. Right? Let me put in that extra step for you. Times 1 over b to the power of c, which means b over a divided by b over c. So we have a b's on top, and we have c b's on bottom, and we're just going to cancel them out one by one and so on until all the ones in the bottom are canceled out and we're just left with some b's at the top. How many are we going to be left with at the top? A minus c of them. Okay? By the way, this 3.3 times 7, quick way of doing it, 3 times 7, 21. 0.3 times 7, 2.1. Okay? Because it's, as an aside, 0.3 times 7 is 3 times 7 divided by 10. 21 divided by 10 is 2.1. Because you're moving that decimal spot over once. So we have 23.1 times 10 to the power 1. Quick way to multiply a very large number by a very small number. Okay? And that's much simpler than to look at something like this. And ask for the answer. Okay? So, just a reminder of that exponent rule. Let's say we have 10 to the power of 8 times 10 to the power negative 7. That is 10 to the power of 8 times 1 over 10 to the power of 7, which is 10 to the power of 8 divided by 10 to the power of 7. So we have 8 tens. I believe 1, 2, 3, 4, 5, 6, 7, 8. And in the bottom we have 7 tens. 4, 5, 6, 7. And they're all going to cancel out pair by pair until something is left at the top. And that something is 10 to the power of 8 minus 7. That's what you have left after you cancel them all out. Right? 10 to the power of 1. Now in this case, 23.1 times 10 to the power of 1, well, that's just 23.1 times 10, which we can simply write as 231. Okay? But for some calculations, can't really do that. Let's say we have 330 million Americans. If each one were to be given, say, $6,000, how much money would that require? Okay? Well, let's go 3.3 times 10 to the power of 8 times 6 times 10 to the power of 3. And that's just 3.3 times 6 times 10 to the power of 8 times 10 to the power of 3. And now we can easily multiply those tens. We have 8 tens that we're multiplying by, and then another 3 tens that we're multiplying by. We're going to have 8 plus 3 tens as a result. 3.3 times 6, we can use our little shortcut here. 3 times 6 is 18. And 0.3 times 6 is like 3 times 6 divided by 10. 1.8. So we have 19.8 times 10 to the power of 11. And that's our answer. That's how we can quickly, without a calculator, multiply two very large numbers. Okay? Similarly, we can divide. let's say we have 330 million Americans, but they're going to divide up, let's say, $5 million. Okay, $5 million sounds like a lot of money. How much is that money when it's split between 330 million people? Okay, well that's 5 times 10 to the power of 6 divided by 3.3 times 10 to the power of 8. Well, we can split this up. 5 divided by 3.3 times 10 to the power of 6 divided by 10 to the power of 8. Okay? So, we have 5 divided by 3.3 times 10 to the power of 6 times 10 to the power of negative 8. It's the same thing. Let me just put in that extra step for you. 10 to the power of 6 divided by 10 to the power of 8. Right? And now, 5 over 3.3 times 10 to the power of 6 plus negative 8. Right? We're still adding the exponents. Right? And what we have, 5 over 3.3 times 10 to the power of 6 minus 8. 5 over 3.3 times 10 to the power of negative 2. Or divided by 100. Okay? So, we can calculate 5 divided by 3.3. And you will get, if we round to 2 decimal places, 1.52. So we have 1.52 times 10 to the power negative 2. 1.52 divided by 100, which means we're moving the decimal spot over twice to the left. 0.0152. Right? We move it over to the left once and twice. So $5 million is actually just over 1 cent per citizen, as an example. So, with scientific notation, multiplying and dividing very large numbers, very small numbers by each other becomes a much simpler calculation, because you just have the leading numbers being multiplied or divided, like 5 divided by 3.3, or 3.3 times 6, right? Much simpler calculations. And then how you deal with the exponents of 10, you just add the exponents. Or with negatives, you're subtracting the exponents, which is really just adding a negative number. And that's scientific notation.